Good day, ladies and gentlemen, and welcome to the American Society of Civil Rights Engineers Geo-Institute Earth Retaining Committee web conference. To submit a question or comment at any time during the presentation, please click on the Ask a Question button on the bottom of your screen. At this time, it is my pleasure to turn the floor to your host, Glenn Anderson. Sir, the floor is yours.
Thank you. Don't worry, this is the American Society of Civil Engineers, not civil rights. But we do believe in civil rights for everyone. Welcome to today's Geo-Institute web conference on from the Earth Retaining Structures Committee. This is our second web conference. The last one was very successful last year. I am Glenn Anderson, and I am the Vice Chair of the Geo-Institute's Earth Retaining Structures Technical Committee. We have 6 presentations for you today. Each one of these will run approximately 15 minutes, with an additional 5-minute period for questions and answers. And if you have questions during the course of the presentation, please submit them through the web page. Before we get started, I would like to recognize our sponsors for this web conference. Our first sponsor, our gold sponsor, is Hayward Baker. Hayward Baker is North America's leader in geotechnical solutions, with a network of offices across North America, each with direct access to the largest geotechnical knowledge base in the industry. Hayward Baker is ready to respond with the optimal solution wherever the location, whatever the size, whenever required. Solutions include foundation support, settlement control, ground improvement, slope stabilization, underpinning, excavation shoring, earth retention, seismic liquefaction mitigation, groundwater control, and environmental remediation. Hayward Baker is part of the connected companies of Keller, a multinational organization providing geotechnical construction solutions throughout the world. Our silver sponsor today for this presentation is Deep Excavation. DeepX is the ultimate deep excavation software developed by Deep Excavation, LLC. It has been used in more than 10,000 projects worldwide, including the new Los Angeles subway stations, the new Tappan Zee Bridge cofferdams, new metro stations in Istanbul, Turkey, the new Panama Canal, and many more. See why DeepX is used in major projects. Please visit deepexcavation.com and ask for a live one-to-one web meeting with our expert engineers. We have another silver sponsor today, Haley & Aldrich. Haley & Aldrich Incorporated is committed to delivering the value our clients need from their capital, operations, and environmental projects. Our one-team approach allows us to draw from our 600 engineers, scientists, and constructors in nearly 30 offices for creative collaboration and expert perspectives. Since our founding in 1957, we have one goal in all that we do: deliver long-term value efficiently, no matter how straightforward or complex the challenge. We also have some bronze sponsors today, the G2 Consulting Group and Itasca Consulting Group. And as I mentioned earlier, our silver sponsors are Haley & Aldrich and Deep Excavation, LLC, and our gold sponsor today is Hayward Baker. We would like to present our first speaker, Wystan Carswell, who's going to be speaking on selection, design, and performance of earth support systems in the South Boston area. Wystan received her doctorate from the University of Massachusetts Amherst in 2015, specializing in soil structure interaction analysis and design for offshore wind turbine foundations. She has continued to focus on geostructural problems since joining the Boston office of Haley & Aldrich in September of 2015, working primarily on excavation support system design. We'll now turn the time over to Wystan for her presentation.
Thank you for the introduction, Glenn. So this afternoon, I'll be talking to you about the selection, design, and performance of earth support systems in the South Boston Seaport area. I'll begin by giving you a brief introduction to the history and geology of the South Boston area, and then summarizing some of the key lessons learned from Haley and Aldrich's experiences with deep excavations in the South Boston area, including some methods for controlling wall movement. Unfortunately, in 15 minutes, I won't be able to get into too much detail on any of these things, so I encourage you to ask questions for discussion later. You may hear me use the acronym SOE during the course of this presentation for support of excavation. So to set the stage here, Boston is a city in the state of Massachusetts on the east coast of the U.S., adjacent to the Atlantic Ocean. And we're focusing just on one small area of Boston, South Boston, which is the orange highlighted area in the bottom right hand of your screen. What makes Boston a really interesting city from a geotechnical perspective is that most of the current day city is actually filled land. For South Boston, that land filling process happened over the course of approximately 30 years, during which the methods, technology, and materials used for filling Boston changed significantly. What that corresponds to is a fairly heterogeneous layer of fill and cohesive fill at the top of a typical subsurface profile for the Boston Seaport area. Beneath those layers of fill, there are sometimes small layers of organic deposits, followed by a sandy or silty layer of marine deposits, and then a deep deposit of Boston blue clay. You'll hear a little bit more about Boston blue clay from my colleague Jean-Louis Locsin later in this web presentation. Approximately 100 to 120 feet below ground surface, there's glacial till and bedrock. But the big takeaway here is a very deep deposit of Boston blue clay. Development in Boston's Seaport area was kicked off by early infrastructure investment, primarily from the Central Artery Ted Williams Tunnel project. In this figure that I'm showing, each of the dots represents a soil boring. So you can see that there were hundreds, if not thousands, of soil borings taken for this project. And following on the heels of that was an extensive soil testing program. What I'm showing here are a brief excerpt from an ASCE Geo-Institute sponsored Geo Congress of 1998 proceedings paper, which shows the undrained shear strength profile for some samples taken in the South Boston Special Test Site. The only thing that I want you to take away from this is that you'll notice undrained shear strength, for the most part, is higher at the towards the top of that Boston blue clay layer, and then tends to be smaller as you increase in depth. Haley and Aldrich has a lot of experience with deep excavation in the South Boston Seaport area, here highlighted in blue. Another piece of infrastructure project that also came through and provided a wealth of information for geotechnical engineers in the area is the MBTA Silver Line, which passes basically through the center of the Boston Seaport area. It would take all afternoon or perhaps more for us to talk about all of the things that we've learned from excavations in Boston Seaport. So I'm going to try and summarize some of our biggest lessons learned by using two example excavation projects, which I'll call Project A and Project B. Chronologically, Project A came first, followed by Project B. And Project A was relatively large, 180 feet by 220 feet, and approximately a 30-foot excavation. But Project B was much larger, 210 feet by 570 feet, and about 10 feet deeper than Project A. You'll notice in both of these cases that the excavation goes plus or minus to the top of that Boston blue clay layer. So, starting with Project A. Project A was supported by a steel sheet pile wall with one level of internal bracing. We monitored the excavation using inclinometers installed at several positions outside of the sheet pile wall around the site and monitored throughout the course of construction. As we were monitoring, we got some deflections that were not quite anticipated. So you can see this inclinometer shows 8 inches of deflection at one location along the site. You can see the small schematic on the right-hand side of the screen, which shows the maximum deflections from inclinometers around the site. While this figure looks very dramatic, what you should also keep in mind is that the scales of my axes are very different. I've got inches, so up to about 8 inches on the x-axis, but this inclinometer is 130 feet long and is towed in those very stiff glacial till deposits. So this isn't something that came out of nowhere. We were watching this story unfold throughout construction. What I'm showing here are inclinometer measurements over time at designated elevations. And each of my grid lines represents a month of construction time. So, we saw the deflection progressing as construction proceeded, and then saw deflections really take off after we reached the bottom of excavation, which was approximately 31 feet below ground surface. At that point in time, we increased the frequency of our construction monitoring to make sure that those deflections weren't accelerating, which would have indicated an approaching failure situation. At this particular inclinometer location, we were able to backfill up 7 feet against the steel sheet pile because it was near the construction ramp. And once that backfilling occurred, you can see that the deflection of the sheet pile wall stabilized. In another location on site, we actually accelerated construction to get the mat foundation in as quickly as possible. In both of these situations, either backfilling against the sheet pile wall to keep soil levels high or placing a mat foundation, both of these resulted in controlling excavation wall movement. So what are the consequences of 8 inches of deflection in your SOE wall? Well, there was surface cracking on the street, and there was ground settlement, and while the city was not too thrilled with these results, what you should also know about this excavation is that at the time that this parcel was being developed, there were virtually no other major buildings in the area. So you can see in this aerial view of the Seaport area that most of this was parking lot. Additionally, the client owned the parcel, one of the parcels directly adjacent to this Project A, and they already knew that they were going to be replacing the utilities in the street. So really, this was an opportunity to push the envelope a little bit with the excavation support system and to be a little bit more aggressive in assumptions for soil properties. But, how do you get to 8 inches of deflection? Like I said, possibly soil properties were too aggressive. Additionally, and definitely a large player in this case, the SOE system was not stiff enough. So, for instance, they could have used a heavier sheet pile or a concrete diaphragm slurry wall or multiple levels of bracing. Another contributor could have been consideration of global effects, so deep-seated movements in that Boston blue clay and or time-related effects for how quickly the excavation was proceeding. In reality, it was probably a combination of all of these things. So, moving on in time to Project B. So, Project A happened first, followed by Project B. Project B was that much larger excavation that was also approximately 10 feet deeper. In this case, a concrete diaphragm slurry wall was used with multiple levels of internal braces and tiebacks. So this is a much stiffer SOE system than Project A. What was interesting about this is that the wall performed as designed, but we also saw evidence of global soil movements in our inclinometer plots. So this inclinometer is showing approximately a ½ inch of movement as much as 100 feet below ground surface. So that's showing that global soil movement of soil behind the wall, pressing down and coming around and wanting to come up inside the excavation, which you'll remember is a very large open area. Another thing to note is that at the bottom of this inclinometer, we assume that the inclinometer is fixed. However, this looks more like a pin connection than it looks like a pure fixity. If I just gave you this inclinometer plot, you might be concerned that the entire wall was translating. The only way to ensure against that is to back up inclinometer data with high-quality survey data of the top of the inclinometer. That way, you have a second point of validation so that you can track your inclinometer as excavation proceeds in case you do have these types of deep-seated movements. So the deep-seated movements can also be a function of strain softening. I've got a schematic to the right which indicates possible behaviors of strain softening for soils. And for those who aren't as familiar with strain softening, that what it basically means is that for no change or very small changes in stress, you can get much larger increases in strain. So intuitively, you can see how construction time might play a role in the straining of your soils. Moving on to the ground settlement data, if you imagine that inclinometer plot flipped 90 degrees now, and we saw that ½ inch of deflection approximately 100 feet below ground surface, that's something that you also then see in the ground settlement data. We did see a ½ inch of settlement 100 feet away from our excavation. In fact, we also saw a ¼ inch of settlement up to 250 feet away. So this really underscores the importance of looking at deep-seated movements and global stability. So, to summarize, it's really important to know your soil in a deep excavation area. And part of that is the subsurface investigation, also soil testing. And then, even more importantly, I would argue, is understanding the soil models that you're using for design and analysis. You need to know basically what you do know and what you don't know in terms of what those models are or are not taking into account. Secondly, instrumentation and monitoring are critical for these types of projects. In the best case scenario, they are a validation of your design, and in the worst case scenario, they give you the opportunity to react before long-term project issues arise. I also proposed 2 methods for controlling wall movement. One of them was to pour a mud mat or install a mat foundation, and the other is to control the open excavation area. So, for instance, you could excavate in slots or phase the excavation around your plan. Lastly is a caveat to beware of deep-seated movements. So the local support of excavation analysis really is just one part of the design. And as a geotechnical engineer, it's really important to also look at those larger global effects, which take into account construction time and geometric effects. So checking global stability and basal heave is really important in looking ahead on how your project will perform. And with that, I will conclude. Thank you. This is an aerial view of what the Boston Seaport looks like now, and I will take any questions that you may have.
Okay, thank you, Wystan. It looks like you've got a few questions, and we have about 5 minutes.
Okay. So, one of the questions is inclinometers of Project A also seem to show rotation at glacial till and about 0.6 inches of movement at depth. Is this real? I think that's a really great question. It was difficult to see in those inclinometer plots, so I applaud you that you were able to catch that. With the scale of 8 inches, it's difficult to see that 0.6 inches or, approximately ½ inch of movement. There were global effects in the same way that I pointed out with Project B in those inclinometers for Project A. So I would say the answer is yes, that was real, and the reason why we could see that is because of, again, the validation with high-quality survey data at the top of the inclinometer. So another question that came up is, why didn't you take the slurry wall several feet deeper compared to the excavation depth? That's also a good question. In this case, it is basically a question of risk and price. So obviously, the deeper the slurry wall, the more expensive the system is. And in the case of these global movements, a couple feet deeper probably would not make a very big difference in these types of large movements. So really, in order to mitigate that type of behavior, you would need to be taking all or some or periodically some of those slurry wall panels all the way down to rock, which now becomes a very expensive proposition. I think I have time for one more question.
You've got 3 minutes, Wystan. Okay. You have 3 more minutes.
Oh, great. Another question that came up, let's see, so how deep were the sheet piles for A and B is one of the questions. I don't have that off the top of my head, but I will say, again, for Project A, there were those steel sheet piles, and Project B was the concrete diaphragm wall. Very broadly speaking, for Project A, it was about 20 feet of embedment for the steel sheet pile, and for Project B, it was about the same, 20 feet of embedment. I guess I will conclude with saying there are other methods to control wall movement, like we discussed with taking the slurry wall deeper. So one option is to take a slurry wall down to rock, and another one, for instance, would be to do a ground improvement or soil mixing program, both of which are very expensive propositions, or much more expensive propositions, I should say, and come into a conversation of risk with the client and what the client is willing to adopt in order to move a project forward.
Okay, well, thank you, Wystan. That's a very interesting presentation. Our next presenter will be Doug Chappell. Doug is with Worcester Engineering. He currently serves as a Vice President of Worcester Engineering and Construction Incorporated. He has a degree in mining engineering from the University of Missouri at Rolla. Prior to working with Worcester, he was an engineer in mines in North and South America, as well as serving as an engineering manager for a regional geotechnical consulting firm. Mr. Chappell is currently responsible for engineering and project management for Worcester and has designed and managed hundreds of geotechnical construction and ground improvement projects in the Southeast. We'll now turn the time over to Doug for his presentation.
Thank you. Going to do kind of a project case study here. A project located in Greenville, South Carolina. Just informationally, it's in the Piedmont Geotechnical Province, silty sand, sandy silts. We're generally dealing with soils with fairly high shear strengths, really good strength values. So we do a lot of soil nailing and things like that. We can use systems that are a little more flexible than what you might have seen in the previous projects, and sometimes we can push the envelope a little more cost effectively. So this project, it's the I-85-385 Gateway project, located in Greenville, South Carolina. It's an interchange project. It's currently the most expensive design-build DOT project in South Carolina to date. Heavily trafficked interchange between two interstates, and they are altering it from its current configuration to this new flyover configuration. To do this, obviously it involves quite a few bridge structures and new roadway structures. A little more specifically, replacement of 5 miles of roadway, construction of 10 new bridges, widening 2 existing bridges, roadway widening beneath 1 existing bridge, construction of new embankments over 50 feet, and construction of new M.ASCE walls in excess of 50 feet. So as a member of the project team here, we came up with some design-build concepts for some earth-retaining structures that I think were a little outside the box and save the project some money and time. One of these was a wall called Wall 32. Widening of I-385 in one section required a new embankment about 60 feet height on each side. They decided to do this with M.ASCE panels instead of doing a sloped embankments. The existing travel lanes had to remain open. The max embankment heights were on the order of 50 to 60 feet, with a total length of this embankment, or M.ASCE wall system, of about 1,100 feet. So to install this full-height M.ASCE system, it would have required one of 3 things. In order to keep the travel lanes going, either a 50-foot tall rigid temporary shoring system, i.e. sheet piles, H-piles, tiebacks, the whole thing. Lay back into the existing travel lanes, which was clearly not an option to maintain travel, or what we decided to utilize was a shored mechanically stabilized earth wall. For those of you who are not familiar with those, this is actually it's an NCDOT concept of it. So basically what's the concept of the shored M.ASCE wall is you install a permanent soil nail wall into these cut slopes. You utilize the permanent soil nail wall to account for the global stability of the system. So you can shorten up your strap lengths when you build the actual wall. So instead of a wall with 60-foot wall with strap lengths of 60 feet long, now maybe you're building a 60-foot wall with strap lengths of 30 feet long, going a little longer up over the top. And that obviously is a little more cost effective. And the added benefit is then when you're excavating, this permanent soil nail wall can act as a temporary support. So here is the existing travel lanes. On this next side, the red line is basically the location of the M.ASCE wall face. The blue line on this next slide was the location of what we called Wall 32, or the soil nail wall for the shored mechanically stabilized wall system. Soils on the site consisted of typical embankment fill, fairly clean embankment fill in most areas, underlain by residual soils and then PWR, so fairly typical profile for here. Here is one of our slide runs. Obviously, you can see the soil nails toward the back there. This is a static run, so safety factor of 1.5. You can see the nails are capturing the global circles, and the straps deal more with the internal stability of the system. Here's a pseudo-static run, safety factor of 1.1. So I know obviously we're dealing with seismic force resisting as well. So this slide is just a general wall design. We had typically 25 to 35 foot nails, generally 5 foot by 5 foot spacing. Wall heights again from 10 to about 35 or 40 feet. Here's some of our construction phase photographs. Obviously our soil stands up pretty well for us. We're nailing embankment fill. It was actually fairly confident. We did run into some debris in some areas, but nothing we couldn't fairly easily work around. Here's our end result. Again, we don't need a terribly planar finish because the whole thing's being buried, but we do need to encapsulate the nail heads for corrosion. Now we get into the M.ASCE wall construction phase. As you can see, the panels on the left and the soil nail wall on the right. Select fill in between. Here's another picture of it. The roadway would be on the upper left there at the top of the embankment. This gives you an idea of the scale of the wall during construction, so probably not a record-setting wall, but a fairly tall wall. You've got your straps running back to the soil nail wall. There's an FHWA manual on SMSE systems, and obviously there doesn't need to be a positive connection between the soil nail wall and the straps. And there is your finished product. So now moving on to another challenge we had in the project. This is what's called Woodruff Road Bridge, heavily trafficked main thoroughfare in Greenville. This bridge goes over 385, and the intent was to widen that. So you'd have 2 more travel lanes on either side. Here's your existing structure, supported by timber piles, well, a combination of driven timber piles and driven steel piles, supporting the indents and just an embankment. So to widen this, we had to basically cut down right in front of the existing abutment and create a retaining system. So your existing condition, obviously typical concrete bridge, concrete-faced sloped abutment. So this shows you the existing condition and kind of the challenge we were given. We have these driven timber or steel piles, of course in alternating batter, one vertical, one battered, driven down to weathered rock, but the bearing surface of those piles was above the new roadway surface because they hung up in this shallow weathered rock. So here is what the proposed new condition was: a wall directly up against the abutment. Obviously, the existing timber piles projecting through the face of that wall. So you have an issue of the timber piles being in the way, and also as you work your way down, you're going to undermine the support of those timber piles. So we took that opportunity to come up with a solution that seems to have worked fairly well. The department did not want us attaching positively to their bridge or abutment in any way. We suggested perhaps going through the bridge deck or attaching to the new abutment, but they did not want to do that. So what we proposed was a micropile supported new pile cap with a haunch on it to grab the existing pile cap, and then a series of tieback anchors into that to basically provide support for the bridge. This allowing us to work our way down and actually cut off the existing battered timber piles on our way down, of course with temporary support in the interim phase, and install a soil nail wall to create the retaining structure. Our general sequence, install and test micropiles to make sure we have adequate support there. Excavate the first stage of our bent camp. Temporarily support the individual timber piles as necessary with hydraulic jacks. So the battered piles that we would actually have to cut, we would use jacks to support these, and they would eventually get cast into the beam itself. Install the micropiles. Remove the battered timber piles as necessary to allow for the grade beam reinforcing steel, because they didn't want, obviously, timber piles in a new grade beam for corrosion concerns. Cast the stages of the grade beam. Install our tiebacks. We actually staged the grade beam excavation and construction, so we didn't have too large of an unsupported area at once. Proof test and lock off the tiebacks, and then proceed our way down in 5-foot lifts, installing our soil nail wall. Here's a little more detail on what we wound up doing. Again, you see the battered piles that we had to cut off, grabbing it all with the haunch and the tiebacks. And you can see the micropiles there as well. Here is a top plan view of the existing abutments. The hatched piles were the battered piles that had to be cut off and removed. Obviously, every other pile or every third pile in some areas. So sequencing was very important. Here is the start of our work. Obviously, access is a bit difficult because we can't dig more than 4 or 5 feet at a time, so we had to use a limited access micropile drill to install these micropiles in some fairly tight spacing. As you can see, you have a micropile installed, and as you work your way to the right, you can start to see the existing piles excavated. Again, we work in soils, fortunately enough for us, that have fairly high shear strength values. So here you can see we're able to make these nice 5-foot cuts, and here you can see the battered piles projecting through the wall face. Those were later supported by jacks and cut off. Here's a section where they had actually driven steel piles. As you can see, here's our forming of the grade beam, micropiles protruding into it. Grade beam was cast and the tiebacks were installed in tension. So now we have secured the abutments. Of course, we've got to stage our excavation appropriately on the way down so that we don't cause bending issues with the micropiles. We can't go in there and make 7, 8, 9-foot cuts and expect those piles to do their job without some buckling. So we had to control the grading contractor on that end. And here we are working our way down with our soil nail wall. You can see the new cap at the top and the soil nail wall as we work our way down. Another construction phase photo. And here is the end result. So instead of having an embankment there, you've now allowed for 2 travel lanes and captured the existing bridge. So all in all, we feel like it was a pretty good solution for everybody involved. So thank you. Obviously, we had designers, SCDOT, the contractors, Flatiron and Zachary. We appreciated all their help on the project. So with that, I'll answer any questions.
Okay, well, thanks, Doug. It looks like you have a few questions there if you want to go over and read them and answer them for the audience.
What software was used for the global stability? That was actually our consultant that utilized that. We use Slope W typically internally. I believe this was done with Slide. The resistance factors, as far as factor of safety, there is with the soil nails, those resistance factors typically relate to the nail pull-out resistance factors. But the factor of safety, you can see it on the output there. For the static case, it was 1.5, and pseudostatic, we were right at 1.1. Do permanent soil nails need additional material requirements? Yes, and that relates to corrosion resistance. So what we have there is, when the soil nails don't have to be any longer because the thing has to be equally stable, whether it's temporary or permanent. So you have to use epoxy-coated, typically epoxy-coated bars. SCDOT preferred a galvanized bar, so we installed galvanized soil nails. And when you install the permanent system, you need to corrosion protect your plates and nuts on the end. So those were the bumps you saw on the wall there. How long was the construction phase? Construction phase, this job is about a 3.5-year job. Some of our temporary support systems, they would have to be in service for 2 to 3 years, but these were actually permanent systems. So they have, 50, 100-year design life, whatever was dictated by the FHWA. What was the size of the micropile and length? Our micropile lengths were probably about, I believe, 35, 40 feet, because we get into that weathered rock, and then rock usually follows fairly rapidly in the Piedmont here. We were using about a 5-inch micropile. We initially were going to install a cased pile with bar, but we got into some difficult drilling conditions, so we used a hollow bar pile, but we had to make sure we used a hollow bar pile that would provide sufficient section modulus to endure the temporary bending conditions as we excavated our way down. And I think that's all I've got as far as questions. Thank you very much.
Well, thank you, Doug. That was an interesting presentation. Our next presenter is Jean-Louis Locsin with Haley & Aldrich. Jean-Louis is a geotechnical engineer at Haley & Aldrich. He joined them in 2005 after earning his master's and Ph.D. in civil and environmental engineering from MIT, my alma mater, I have to say. Over the last 12 years with Haley and Aldrich, he has had the opportunity to work on numerous bridge and building projects, many in the northeastern United States, and he is a licensed professional engineer in the Commonwealth of Massachusetts. So we'll now turn the time over to Jean-Louis.
Thank you, Glenn, for the kind introduction. Hello, everyone. Today, I'm going to talk about the successful implementation of ground movement control measures for deep excavation in Boston Blue Clay at the 1 Dalton Street project. Let's quickly go through the outline of the presentation. First, it's just a brief description of the Four Seasons 1 Dalton project. Then I'll talk about the challenges that we faced, the geology encountered at the site, the excavation and the choice of excavation support, measured lateral wall movements and vertical movements of adjacent structures, and lastly, some conclusions to close. The Four Seasons 1 Dalton project consists of a tower with a 5-star hotel and luxury condos. It's located in the Back Bay area of Boston, Massachusetts in the U.S. The developer is 1 Dalton Owner, LLC. The architect is Pei, Cobb, Freed, and Partners, working with Cambridge 7 Associates, which is a local firm here. The structural engineer is WSP out of New York City, and the geotechnical engineer is Haley and Aldrich. A rendering of the finished tower is shown here with an arrow for those who are unfamiliar with the Boston skyline. The project is estimated to be completed in 2018. It will be 61 stories high, about 770 feet tall, and at the time of its completion, it will be the 3rd tallest building in Boston. There will be 3 levels of below-grade space, and the building will be supported on rock-socketed deep foundations. We faced a number of challenges on this project. First, the relatively small triangular site. It's about 28,000 square feet in planned area here. The street with the white cars that you see there, that's Belvedere Street, and the street along the upper side of the triangle is Dalton Street. Then there's construction in a busy urban environment. That's Belvedere Street there with the white taxis, which you saw in the previous picture. And it's usually a pretty busy street. And as you'll see a bit later, the excavation is pretty deep and it's conducted in soft soil. Another significant challenge was protecting this 5-story concrete building right next to the excavation. The building is on shallow foundations, which would be vulnerable, especially during the excavation stage. So remember that ground surface here is about elevation 17.5. The geology at the site consists of fill, followed by organic deposits, marine sand, and a sliver of marine silt. Then you have the Boston Blue Clay, and it's typically composed of about 5 to 10 feet of over-consolidated clay, which we call a crust, followed by a very soft material, usually weight of rod or weight of hammer material. And then you have glacier marine deposits and bedrock in red. Bedrock is typically argillite in this area. The excavation went down to about elevation minus 30, so remembering that elevation, ground surface is at 17.5. That's a depth of about 48 feet. The bottom of the excavation is in the soft clay, and essentially the 5 to 10 foot thick clay crust is removed. So you can't rely on it for any lateral support. Furthermore, the adjacent concrete building is supported on shallow foundations in the marine sand, and those bear about 20 to 25 feet above the bottom of our excavation. So it's not good. That's very challenging. So as far as the supportive excavation elements, They were selected based on their ability to limit movement, but here they also doubled as foundations or load-carrying elements. The two sides of the excavation use load-bearing walls, or LBEs, as we call it here. I think it's barrettes in other parts of the world, and slurry wall panels. And these are shown in orange or dark orange and yellow, respectively. The slurry walls and LBEs are basically rectangular reinforced concrete elements. LBEs carry high loads and are socketed into rock, usually. And then the slurry walls may carry some load, but much lower than the LBEs. And those, in this case, terminate in the clay. A secant pile wall was also used along the side of the excavation that's next to the existing building, as you see there. Secant pile walls are normally composed of overlapping concrete elements with embedded heavy steel sections. In this case, that wall wraps around the corners of the excavation, and those meet up with the slurry wall and LBE elements on the adjacent sides. The tower core in the center there, you'll see a little triangle. That's supported on LBEs. The supportive excavation included 3 levels of internal bracing, and the wall and adjacent building movements were monitored during construction. During design, our analysis predicted that for 3 levels of bracing, the lateral displacement of the secant pile wall, which is adjacent to that building there, would be about 1.7 inches. We were concerned that this would lead to excessive settlement of the adjacent building given its proximity. Further analysis indicated that to control these movements, the bottom of the secant pile wall would have to be supported laterally before even reaching the bottom of that excavation. So after some discussion with the design team and the owner, we decided that below grade, or what we call subgrade struts, were the solution. So basically, subgrade struts are unreinforced rectangular concrete panels installed below the bottom of the excavation to act as lateral supports for the embedded portion of the wall. Essentially, they're an internal bracing below the lowest excavation level. Here's that excavation plan again, but with the subgrade struts shown there. There are a total of 7 subgrade struts. Let me advance. So 2 of those struts connect to the LBEs on the adjacent side there. And then the rest, or 5 of them, basically terminate in the soil. So the longer ones that attach to the other sides are about 70 feet long, and these yellow ones that terminate in soil are about 32 feet long. These yellow ones rely on friction on the sides and on the bottom of the strut, friction with the soil. Now let's look at the sequence of how these struts were installed by looking at this section AA here. So starting from the installed secant pile wall, the adjacent 5-story building is on the right there in gray, and the existing mat was cut off and removed. They excavated to about elevation 2, and then from there, the subgrade struts were installed using slurry trench methods. The top of the strut is about -31, and the bottom is about -47, so that's a 16-foot high subgrade strut. They're about 2.5 feet wide and made of 2,500 psi concrete. From elevation 31 or -31 up, that trench is filled with cement bentonite, so it's easier to excavate as they come down with the actual excavation. From that point on, the excavation proceeds as, quote, normal. So you have the first brace installed, and then you excavate down to -5 in this case. And remember, ground surface around the site is at 17.5. Then you have the second level of bracing, excavate down to the next level, third level of bracing, and then excavate down to the bottom of the excavation. So you see the subgrade strut is just below that starting. So how did the secant pile wall perform with the subgrade struts in place? Well, we did monitor the wall performance using inclinometers, which are basically instrumentation installed in the wall to measure lateral movement. Here's the data from the inclinometer in one of the secant pile wall or secant pile elements that went into rock. That's about 1 in 5 of those elements along that wall. Note that the secant piles in the clay, they terminate at around -48 there, shown in red. The lateral displacement is on the horizontal axis there, if you can't see it, and the elevation on the vertical axis. All the curves shown except for the blue diamonds there, well, those are measurements after reaching the bottom of the excavation. The maximum wall displacement that we saw was less than 1 inch, shown by the red line there. And I superimposed the location of the subgrade strut here with elevation, and you can see the impact of the subgrade strut. It's pretty apparent in the shape of the displaced curve here. Now, vertical movement was also, vertical movement of the adjacent building was also monitored. And here are some vertical displacement measurements at 2 survey points on the adjacent building on the side closest to the secant pile wall. I'm superimposing the secant pile wall installation period here. That process actually led to about 4/10 of an inch of settlement. Then, after reaching the first excavation level with the first level of bracing, that's another 1/10 of an inch, thereabouts. Second level of bracing, that's another 1/10 of an inch. Third level of bracing, another 1/10 of an inch, seems like. Then reaching the bottom of the excavation, that's another 1/10 to 2/10 of an inch. In total, the settlement was measured to be about 1 inch on that side of the building closest to the excavation. So some conclusions. Well, first, excavating through the clay crust basically increases the risk of excessive movement, both laterally of the wall and any vertical movement of adjacent structures. And to control the movement, we decided that subgrade struts that were installed before excavating down to the bottom were necessary. Roughly 50% of the measured movement, the vertical movement, occurred during installation of this secant pile wall, and that's really very difficult to predict. The owner and design team chose to be proactive to mitigate movement and reduce risk by constructing these subgrade struts. So rather than be reactive, and see what happens and then take care of it, then, the owner and the team decided to install these elements. And then subgrade struts were effective in controlling lateral movement of the wall below the bottom of the excavation, and that resulted in vertical movement and also limiting the movement vertically of the adjacent structure. So here's the construction as of April of this year. So they're out of the ground, and thank you. And I will take questions.
Hey, thanks, Jean-Louis. That's very interesting, and it looks like you've got some questions, so go right ahead.
So the first good question here, how is the contact made between subgrade strut and the secant piles? So that's a really good question because this idea is great, but if you leave any slack between the subgrade strut and the secant pile, then it's pretty much useless. They basically attached a fitting to the side of a clamshell bucket that followed the shape of the secant pile wall. So it was scraping against the secant pile wall as it went down to dig the hole or the trench. So that ensured that there was no slack between those two elements that would be compressible. So that was a really important aspect of the construction of those subgrade struts. Did the shorter subgrade struts use passive resistance for lateral support? That's a good question. The ends of those would have been roughly, 2.5 by 16 feet high, but the length of them and the contact for skin friction was was pretty significant, so we did not explicitly use the passive resistance at the tips of those and designed those mostly using friction. Another question, what were the loads on the LBEs? The highest loaded ones I remember are about 10 to 15,000 kips vertical load. And I think the secant pile elements, the ones that went to rock, were about 1,500 to 2,000 kips. Another question, why not extend the struts to the core LBE elements? The structural engineers didn't really want to do that. They did not want any lateral loads on those core elements. So we said, okay, and it worked out. How much did the subgrade struts cost? We estimate, I think it was like $1 million for that. What other options were considered? Well, we did look at other things such as ground improvement, deep soil mixing, jet grouting, but in the end, I think the logistics and the cost of it, and the fact that the equipment for building these subgrade struts was already there because you're installing LBEs and slurry walls, that made it much more attractive, and the impact to the schedule is much less. Was there a backup plan?
You've got a couple more minutes, Jean-Louis.
Okay. Was there a backup plan if there was movement even with the subgrade strut? Yes, there was. Actually, we were thinking if we were seeing movement that we would probably trench all the way to the core LBEs. Was the adjacent property owner okay with 1 inch of settlement? Well, the thing is, the other side of the building didn't really, that was surveyed as well. The building is about 120 feet wide, if I remember correctly, probably more. The other side of that building didn't really experience any settlement. So between that side and the side closest to the excavation, given the fact that we were basically cutting off their foundations and really right up against the structure, there wasn't any negative impacts to the building, so that didn't really hinder or delay construction.
You've got one more minute. You've got one more minute if you'd like to answer another question.
Were the subgrade struts reinforced? No, they were not. They were purely compressive elements, so we didn't think that they needed to be.
Okay, well, thank you, Jean-Louis, for your presentation. That was very interesting. I'm not sure that many of us have seen that application of subgrade struts. It causes us to think. Our next presenter, actually our next presentation was prepared by Augusto Lucarelli. Unfortunately, he's out of the country and could not connect with us, but he has requested that Varun, one of his colleagues at Itasca, join us and make the presentation. Varun is a geomechanics engineer with a specialization in geotechnical earthquake engineering and soil dynamics. He received his Ph.D. From Georgia Tech and has been working with the Itasca Consulting Group for the last 7 years. So we'll now turn the time over to Varun.
Thanks, Glenn. Thanks for the kind introduction. As Glenn already said, I'll be presenting. This work was originally done by Augusto Lucarelli, who's one of my coworkers, and I'll be presenting in his place. So what I'll be talking about in this presentation is jet grouting applications for earth retaining structures. There are 3 examples that I'll be talking about in this presentation. Most of the time we'll spend on the De Lelli Underground Park in Verona, Italy, And then I'll talk a little bit about two other applications, one for the Repubblica underground part and one for a cut-and-cover tunnel in Milan. So this is the general outline for that the first project, which was an underground park in Verona, Italy. It was a reasonably big area, about 3,000 square meters. The excavation depth was still about 13 meters deep. The soil was mainly a mixture of gravel and sand with cobbles. It's hard to excavate. The company that was doing the construction was the Keller Group, which is the Italian branch of the main Keller Group. So they initially thought of concrete diaphragm wall, but it wasn't feasible because of all these cobbles. The micropiles were turning out to be very expensive, so they proposed jet grouting, and they wanted to do a proper evaluation, so they hired Augusto to do the numerical modeling for this. So this slide just shows the job site during construction, so you can see the excavation after the wall had been put into place. What you can also see is once they did the jet grouting, they also did some testing to get an idea of the quality of the jet grout. So the quality was actually very good. The UCS that came out from this was about 15 MPa. We only needed about 4 MPa for the design, but the fact that it had all those cobbles and gravel really helped, because what we ended up really was almost the strength of a lean concrete. This slide just shows the overview of soil conditions. So we mainly had sand and gravel in the top, underlain by silt with clay layer, and and below that was a very dense sand and gravel layer. The SPT values for this are shown. They were about 50 to 60. So you can see it was very firm ground, hard to excavate. And on the right side, we also are showing shear wave velocities measured from M.ASCE. You can also see on the left plot, it shows the soil treat or the jet grouting wall. It extended all the way up to 15, almost like 14 to 15 meter deep. So the depth below the excavation level was about, or the amendment depth was about 2 meters, which is kind of a little low compared to traditional, but the idea was to create a gravity wall with high thickness to avoid any tension, basically, in the wall. There was no water table, which kind of worked in favor of this technology for this project. I mean, the water table was very low, basically. To do the numerical modeling for this project, we used the plastic hardening constitutive model. Why we didn't use the more Coulomb is it's generally not acceptable when you have both loading and unloading going on, and we care a lot about deformations. The stress path is more complex, and with more Coulomb, you have the same modulus essentially throughout the loading, basically no degradation of modulus with shear strain, and also we don't have a different loading and unloading or reloading modulus. And then when we calculate the stress resultants like moment and shear force, they were underestimated. So if you look at this plot, I'm basically showing in the blue dotted lines the predictions that would have happened had we used more Coulomb model. So you can see there is a lot of uplift that is simulated on the excavation side, and then on the other side also, more Coulomb model predicted a lot of uplift, which was not correct, and then it underestimated the wall deflection. The simulations that were done using this plastic hardening constitutive model kind of are more realistic, and what we are showing here in red are what the results we got from the plastic hardening model, and they are also compared with the results that were obtained at the site, or basically the observations at the site once the project was once this thing was carried out. So you can see that the plastic hardening model did a relatively good job in predicting the deformations and other quantities. Just a little bit of background on this plastic hardening constitutive model. It's kind of used worldwide now. It's well known inside civil engineering geotechnical community. In many areas, such as excavations, foundations, and tunneling, is kind of becoming a standard model now. A lot of regulatory agencies, especially in Europe, now require, or at least strongly endorse, that people use this model instead of more Coulomb, and it's relatively easy to calibrate and use similar parameters as what we get from site investigation and from lab tests. It's available in a lot of software, such as Flag3D, Flax is MIDAS, so you can easily use any one or compare if you want to compare results. And then more information about it, some of the examples and how to calibrate this is available at this link if you want to go into more detail, because I wouldn't get much time to talk about it in more detail. The only thing I am going to show is just the very basic concept of how the model works. So if you look at the figure on the left, it is showing how a typical more Coulomb criteria would be, which is just this failure envelope. As opposed to that, this plastic hardening model has this shear failure envelope, which has a shear hardening yield function. So, and then we also have the volumetric hardening cap yield function, which allows you to consider the effect of over-consolidation ratio when, of soils. And if you look at stress strain response, that's how it would look like on the right side. So more Coulomb is what's shown in the black line. So it's elastic and then perfectly plastic. The unloading, reloading modulus is the same as the initial loading modulus. Whereas with plastic hardening model, you can see you get this modulus reduction as a function of shear strain and then a different unloading, reloading modulus. And this is kind of important to capture those deformations properly. In terms of modeling, we do the stress initialization. For all these kinds of models, it is important that we first do set up the model and initialize the stresses. So we either use elastic or more Coulomb models so that we have stresses in place, because before we turn this model on, we don't want to be changing stresses which are not realistic, because these models are very sensitive to stress history. So, we have all the stresses in place, and then we turn over the model to the plastic hardening model, and then we can assign properties to each zone as a function of depth, or if you have a variation along the horizontal direction as well. So this just shows the jet grouting wall. These were all cylindrical columns. The thickness of the wall simulated in the model was estimated based on this overlap region. So you can see a 1.8 meter diameter columns, and then based on overlap, we used about 1.32 meters as the thickness. This shows the parameters that were used for the wall. So the unit weight is only 15 kilonewtons per meter cube, and it seems a little low because than the original soil, because of all this air that jet grouting uses, the unit weight kind of decreases a little bit. Then we have a cohesion, which is estimated based from unconfined compressive strength, and then we have a friction angle of 38, which is, we use the same value as the existing soil. So you can see that these parameters are already quite conservative. I mean, the real strength might have even been higher, because we know that the UCS obtained was about 15 MPa as opposed to 4 MPa that we are using here. This just shows how the whole excavation was done. So we put in the wall first, then we excavated, installed the first anchor, excavated one more step, installed the second anchor, and then excavated one more and installed the third anchor. This slide mainly shows the deformed mesh, which is the deformations magnified by 100 times, just to show the shape or the mode of deformation, and also the forces. So the maximum horizontal displacements were about 12 millimeters, and the maximum vertical displacements were about 5 millimeters. So they were quite small. This just shows the stress distribution in the jet wall. by integrating the stresses, we also calculate the shear force, the bending moment, and the axial force in the wall, and these are all shown here. Looking at the stresses, you can see stresses are around 600 kPa, which are way lower than the 4 megapascal strength of the wall, so we were well within the failure envelope. And then there's an eccentricity plot just showing the location of neutral axis to make sure that we were not getting tensile forces developing in the wall. So far we just saw the performance. Now the next step was to evaluate the factor of safety, and we used the strength reduction method. The reason why this is better is because you can monitor the structure behavior as you reduce the strength properties. You can track the stress resultants such as forces in anchors, bending moments, and then you can track hierarchical failure, like, do the structural elements have enough capacity, so when the failure occurs, is it the structural elements that start failing first, or is it the soil that starts failing first? So, and then you can evaluate the influence of structural element capacity on the potential global failure mechanism. So another important thing is you can observe displacements, how they develop. So, you can track whether you are satisfying the service limit state and not just the ultimate limit state, because sometimes it might be more critical critical compared to the ultimate limit state. So you can also track multiple failure mechanisms. Most of these things you cannot do with limit equilibrium method and also you have to make assumptions on the forces that structural elements are exchanging with the soil mass. So, and finally, you can do a local strength reduction for a structural element itself or for a limited portion of the model, like a single layer, as opposed to strength reduction for the whole model. So this next slide now shows basically that model just before we started dialing down the strength. So we have realistic stresses in place. We are not making any assumptions about structural element forces. And what we do is we monitor the behavior in terms of the displacements at these 2 points and the forces in the anchors. So this slide basically shows when the failure is about to occur, or right when it's on the verge of failure. You can see the failure surface forming on the top right. You can see that at about this factor of safety, which is 1.65, the displacements suddenly shoot up, which kind of is indicating a collapse. And what you can also see is that the forces in the anchors drop instead of increasing, which kind of indicates that it's not the anchors that are failing, because the whole soil mass is failing. The anchors are no longer being strained or stressed, and they are actually losing that force. So anchors have enough capacity in this case, but the failure mechanism was developing on the soil side. So this is another application which is for Republica Underground Park, and I'm just quickly going to go over this. So it was similar to the other one. There was an excavation. The difference was there were buildings right next to the excavation. So we did the modeling in the same way. You can see in green, on the left plot in green, you can see the jet grouting wall and then the three rows of anchors. And on the right side, you can see the horizontal displacements, which were about 22 millimeters, and the maximum vertical displacement of about 15 millimeters. This is just doing the same factor of safety calculations using strength reduction method. So you can see what the failure mechanisms look like. In this case, we had anchor failures for a factor of safety greater than 1.6. And this one is just showing potential damage to the building using Boscardin and Grouting criteria. So everything is within within the first level, which means minimal damage. On x-axis here is the distortion, angular distortion, and the y-axis is the horizontal strain. This is just another 3D model for that, to look at 3D effects along the smaller extent. So you can see the whole thing was modeled using zones itself. And then we also had the structural elements like piles being represented separately. So most of the details were actually put into a model. So it was a very detailed model. to basically evaluate the performance of these structures due to the excavation. The last one is a cut-and-cover tunnel. So you can see in blue is basically where the jet grouting wall was, and also we had a plug because in this case we had a water level. Our water table was above the bottom of the excavation, so we had this plug to avoid water coming in. And you can also see this stair step thing here, and that was to create this arching effect and transfer the loads to this bottom slab from the side wall. And this figure basically just shows the same thing where we have displacements which were less than 10 millimeters on the bottom right, and on the bottom left you see stresses which show this transfer of stresses from the retaining wall to the bottom slab because of this arching effect. All right, to conclude, jet grouting is valuable and competitive alternative to traditional support systems. It's quite flexible and adaptable to many circumstances and soil conditions. You can use it for sands, and you can also use it for cohesive soils like clays. It can be executed using relatively little equipment, but what it does require is a highly skilled, experienced, and specialized contractor to guarantee high-quality results. And what is also recommended is that one execute field trial tests to calibrate these properties, like the UCS was for this case, in order to get an idea of how good a result are we getting. Next, advanced numerical models allowed us to capture full soil structure interaction, including the evaluation of performance and safety factors. And finally, we recommend using strength reduction method to better understand the potential failure mechanisms and behavior of the individual components. Thanks, and if you have any questions, I'll take any questions.
Yes, Varun, it looks like you have a few questions, and you have about 2 minutes. So if you'd like to go ahead. Okay. What about the tensile strength of the jet grouting? How did this affect the design? So for this case, we did not assume any tensile strength for the jet grout. As I mentioned earlier, the idea for these in these projects at least was to consider like gravity wall kind of solutions and not put the grouting under any tension. On first job, was any 3D analysis done to see punching shear of anchors through jet grout? I don't think so. I'm not sure because I was not the one who did the analysis, but I don't think so. How was the pH model calibrated? I wouldn't go into details for the pH model calibration. I have a link included in the presentation. There were some lab tests, I think, and then there was the in situ test. So the link that I have included has methodology to calibrate using either one of those. Please explain the concept of volumetric hardening cap and plastic hardening model. I'll leave that for the link itself because that's a bigger discussion. Okay, well, thank you, Varun. That was an excellent presentation. Our next presentation is by Pirooz Barar and Babak Mamakani. Pirooz has a bachelor's and a master's degree in civil engineering. He has almost 50 years of structural engineering experience. Started his career with Skidmore, Owens, and Merrill in 1968, and with the last 35 years of his career devoted to the development of advanced technical methodology for design of shoring, underpinning, and geostructures. Mr. Barar is licensed in most of the western United States, central and eastern states, as well as Hawaii. Babak has a master's degree in structural engineering and a Ph.D. in civil engineering from the University of Texas at Arlington. Prior to joining PB&A in 2014, he earned his Ph.D., as I said, from Texas Arlington. He brings to his design team proficiency in the use of specialized analysis programs such as Plaxis and DeepX, along with previous professional experience as a design engineer, project engineer, and field manager. And so at this point, we'll turn the time over to Pirooz and Bobby.
Glenn, thank you so much for a kind introduction. We are going to start by saying that I put in experience first in design and analysis of the retaining system for the Hope Station, because what I believe is that obviously the experience that you have is coupled with the analytical techniques that you use is crucial in the success of a large project that you're going to be talking about. Nobody, we're a small firm, and nobody wants to give you a job if you haven't done it before. In other words, the first question is, in a large project, they would say, have you done something like this before? And in our case would be, yes, we have done that before. So, going to the next slide. We are going to go through some introduction of some of the past experience that we have, and emphasize the fact that designing and successful support of excavation, especially when it goes beyond 60 feet. Somehow 60 feet is a sort of a magical number that beyond that things start becoming unpredictable a little bit. Is that most of these the design criteria was developed about 70 years ago in Chicago and by Terzaghi and many of these principles that were developed are still very applicable and obviously augmented by modern software and you can get better results and better prediction of the stresses and the deformation. But most of if you follow certain very simple, well, not simple, but steps, then the results would be very achievable. But one thing we want to emphasize is that many of the agencies that are owners for these deep or these infrastructures, they still follow that main they follow that principle that was established many years ago, and haven't really, many of these design criteria haven't changed for many years, especially in the case of Metro in Los Angeles. The next slide shows that some of the work that we have done in the past. I happen to have designed the first soil valve in the United States in 1983, and I believe that at that time there was no soil laying in the United States, but I happened to be the first one to introduce the soil laying in the United States. We have got other projects that we have done, such as widening of the 405 freeway in Los Angeles, and also the picture on the right is the Boyd Station, which is a similar project that we are going to be discussing and in this lecture, in this seminar. Looks like we are having a little problem changing the slides. Okay, talking about the Hope Station. Hope Station is a part of the part of the metro extension in downtown Los Angeles. Hope Station is there are two separate lines. One is regional, which is which our part is design of Hope Station, and then from Hope Station the train goes to Broadway, and then there's a west side which includes three stations, La Brea and Fairfax and La Cienega. These are on the now these stations. Hope Station essentially the parts of it that is underneath the Hope Street, but many of these stations are you have to keep like Broadway, both Broadway and also parts of West Side. They are underneath a live street, so the excavation and support of the traffic and digging underneath these stations is a extremely challenging task. And but in this case, in the Hope Station, although it's one of the deepest, which is about 100 foot deep, the area that is the station is located is an intersection of Hope and 2nd Street, and so it is there only a part of it that is under the street. Right now, if you look at the lower picture of the lower left-hand side, there's the station is shown there, and then there's the water treatment plant in the water treatment plant in Los Angeles, and also it's very close by the Disney Disney Concert Hall is right next door. The station is approximately the station is approximately 500 foot long, and about 500 foot long, and consists several. There are several systems of two systems of support of excavation that we have used. This slide is looking that it was animated and doesn't on my screen doesn't look like. It shows the several sections that we are going through the station. The two what we call hammerheads. The train goes from one end to the other, of course, and the two ends are hammerheads, where the tunnel enters and exits. And in this case, we had internal bracing in that area, and then the section that you're looking at right now. One is that we've used tiebacks on most of the station, but also certain areas we used internal bracing to support this excavation. The stratigraphy of the station is that about about 20 to 25 foot of the upper layer is alluvium, and then below that is a Fernando Formation, which is basically a clay stone, and have very high shear strength. What we want to emphasize in here is that the design criteria we use, we basically went through the limit equilibrium and using the criteria that of actual active pressures and being in contact with a deep X-shaft, the author of deep X-shaft, Dimitrios Kostas, we were able to change the parameters or the input of the program to custom design it into the format of the what the criteria was. Another thing that I want to emphasize is that these lateral pressures sometimes are not realistic, because there are two really aspects to the design of supported excavation. One is obviously stresses, but the most important thing is deformation. And a lot of the stresses that are become a part of the design criteria, geotechnical design criteria, is really not a realistic number, but it's mostly just to control the deformation. Now here, I'm going to have Babak come in and explain some of the details of the mathematics and the methodologies that we use.
Okay, thank you, Mr. Pirooz, and hello, everyone. So this is the design criteria. We had a very comprehensive design criteria and design approach report for designing the second and Hope station. So here you can see the apparent earth pressure that we were given to design the SOE. On the left-hand side, you see the trapezoidal earth pressure for the raised excavation, and on the right-hand side, you have a cantilever excavation apparent earth pressure. So as you can see in the left-hand side, the apparent earth pressure above the bottom of the excavation is 24 H, meaning that the pressure is 24 PCF. Then as we go down in the excavation, we have to multiply by the depth of the excavation at each stage of the construction, and then come up with the essentially active pressure or soil pressure. And then we have the active and passive pressure below the bottom of the excavation, as you can see in the small table on each of these scenarios. And then you will find all of these information essentially in the Caltrans and AASHTO standards. Why we have a triangular shape for the cantilever excavation, or the trapezoidal pressure for the braced excavation. So as you can see here, the 24H, we believe that the 24H is a very conservative number given by the Metro. We did the sensitivity analysis before starting the design to essentially prove that this pressure can be reduced to 21H and then can be used instead of 24H. However, at the end, Metro decided to have a conservative design and then use 24H instead. Another criteria that we have was about the lateral surcharges. So one of them was the seismic pressure that you can see here is given in a magnitude of 6H. Again, it's 6 PCF, and then times the depth of the excavation at every stage of the construction. So we usually, in other projects that we don't have the seismic criteria, we use the Mononobe and Okabe criteria to come up with the seismic active pressure. But in this case, we're giving the pressure, equivalent pressure of the seismic, which is 6H. And then another additional surcharge that we were given was the traffic and construction surcharge. As you can see in the left-hand side, it's the 240 PSF at the first 10 feet of the excavation and 100 PSF at the second 10 feet of the excavation. This usually in the Caltrans considered to be 100 PSF of the construction surcharge. Again, this is a conservative number, but Metro preferred to have a conservative number in designing all of these stations down in Los Angeles. And then another surcharge that we considered during the design, as you can see on the right-hand side, is the extra surcharge due to the bench excavation. Sometimes we need to have a wall behind the excavated area, and this second wall actually exerts additional surcharge on the bottom wall, as you can see, and this pressure in this case is called as denoted as B. And if the second wall at the top is away from the active wedge of the bottom wall, then we can ignore it. Essentially, if the distance, which is denoted as A, is greater than the H1 of the bottom wall, then we can ignore that additional surcharge. But other than that, we need to calculate the additional surcharge in this case and put it on the bottom wall. We have many other design criteria. So in this presentation, due to the time limitation that we have, I'm going to just quickly go over some of the important ones. One of them was the embedment depth requirement. So in the design criteria, we're told that we have to at least have 8 feet of embedment where the excavation depth is less than 20 feet. And if it's greater than 20 feet and less than 40 feet, it should be at least 10 feet. And if it's greater than 40 feet excavation, we need to at least have a 12 feet of embedment. So no matter what we get from our software analysis, we have to meet this criteria on top of that. And then the passive resistance that in the criteria, the tributary width of the passive resistance in the design criteria is the 2 times of the drill hole diameter. The drill hole diameter in most of the areas is 36-inch drill hole, which is 3 feet, and the passive pressure can act on the 2 times of this distance due to the arching effect. And then another criteria that we had was for strut design, essentially for the strength-wise. We're asked to design all of the strut system to get nothing more than 12 KSI of stress, but in based on the AIC design and structural capacity of these struts, they can take up to almost 19 KSI. But Metro again wanted to have a conservative design and then limit the stress in all of the struts to 12 KSI, and also limit the slenderness of the struts to 120. And another criteria, an important criteria in this SOA design was to accounting on the negative moment of the soldier piles. So what we did in the deep excave model, we model all of the soldier piles as a simple span beam. Although in reality the beam is a continuous beam, so in the location where we have the support, such as strut or tieback, we can deduct 20% of the moment due to having a negative moment. So as we go down in the excavation, we deducted 20% of the positive moment in the wall. And then in the last one, you can see when the invert slab is poured against the wall at the bottom of the excavation, instead of using a simple span moment, which is PL square over 12, we're told that we can reduce this moment to PL square over 8. So it's almost 1/3 deduction in the moment. So from this point on, Mr. Pirooz is going to take over.
I'm going to interrupt here, just make a couple of comments. One is that these are really simplistic criteria that is imposed, but mostly it works. In other words, it acknowledges that the pressure that is specified at the location of the support is the beam goes through the soldier beam goes through a negative moment, and therefore you can adjust the moments. But it's designed for a simple. In 50 years ago, there were no computers, and you can do that. The second point I want to make is that these excavations for construction of the train boxes, there are two stages. One is to go down. That's very simple. The other one is to come back up, and that's why using the program the XCAV was really crucial in the success of this job, because we were able to, in a normal circumstance, you have to, because this is stage construction as you go down and come back up, and you can calculate all the parameters. And so I'm going to go back and give
Pirooz, this is Glenn Anderson. I apologize, but we've gone over the limit for both the presentation and the question and answer. This is a very interesting project, but unfortunately we have one more speaker, and we only have 20 minutes allocated for him for questions and answers. So I apologize, but we're going to need to move on to the next speaker at this point.
Can we quickly show all the slides in a minute, and then we can close the presentation, move to the...
We're actually over by we're over by 2 minutes now on the next presentation.
Okay, great.
I apologize. Okay, our next presenter is Sean Walsh, and he's going to be talking about some interesting work that's been done in southern Louisiana. Sean is a professional engineer and licensed geotechnical engineer, serving as a project manager for Eustis Engineering. Since joining Eustis in 2012, Sean has provided design and construction recommendations for a multitude of flood protection projects in southeastern Louisiana. The most recent of these comprise multiple segments of the Morganza to Gulf system in Terrebonne and Lafourche parishes. Sean is an active member of the New Orleans ASCE Younger Member Chapter and was recently recognized by ASCE as part of its New Faces in Civil Engineering. He earned his bachelor's and master's degrees in civil engineering from New York University's Tandon School of Engineering. And with that, Sean, we'll turn the time over to you.
Thanks, Glenn. Hello, everyone. All right. So quickly, the agenda, I'll just go over a problem statement that we're facing here in southeast Louisiana, how that's tied in with geotechnical design as us as the geotechnical engineers, explaining how it ties in with a project that we did at Falgout Canal, and then some closing remarks. So it's August in Louisiana. How's that flood wall looking, and how's the gate looking for the next storm event? The ones that have been in place, the ones that have been recently constructed, how are they shaping up? So flood protection, just the word protection is a problem because we're not really guaranteeing protection. We're trying to reduce risk. We're not eliminating it. But like, how can we quantify that? How can we quantify how much risk we've reduced in this particular site versus that one by the improvements that we've made? So there's a lot of people working on that question. There's local politicians, our elected officials, there's structural engineers, there's contractors, there's a whole group of folks working on it. And of course, given the really soft soils that we have down here in Louisiana, geotechnical engineers are also working on that too. So how we can assist with answering these questions is nothing really new, but we're trying to raise awareness now that there's a new breadth in flood protection design, coastal design here in in the southeast Louisiana. So we have soil testing, we can do soil borings, we can do predictive soil structure interaction modeling, as we've been hearing about this afternoon, self-monitoring infrastructure. We can then take all this and review, and we can calibrate and communicate those risks. But really, the best thing we can also do is combine all of our design, our understanding, our history, with empirical measurements, which many of our colleagues across the country and across the globe, of course, they're doing. But this is an unprecedented change down here in southeast Louisiana, which I can explain here in the next slide. So whether it's fake news or real news, both sides of the news, it's all the news. There's definitely, since 1932, Louisiana's, all sides agree, we've lost about 1,800 square miles of land. So from different storms from 2004 to 2008 alone, 300 square miles of marshland were lost to hurricanes Katrina, Rita, Gustav. Major causes, obviously, are climate change, sea level rise, subsidence, hurricanes, storm surges, disconnection from the Mississippi River, and other human impacts. So some of the previous methods of how we've been designing, they need to change as so much of our other coastal conditions are changing. So right now, right after Katrina, we had the $14.5 billion federal stimulus that was put into the city to put up protection systems, and with that came the federal guidelines on how to design these structures. So now that's in place. The federal government put together an incredible set of guidelines, which the system has been put in. It's robust, and it works, and it's been tested. It works well, but it's the top-notch level. And now the nearby local and state municipalities, levee districts, communities are trying to do similar designs because we have the same problem outside of the city, but the funding isn't in place. So right now, to adapt to that, the Coastal Protection and Restoration Authority of Louisiana is really leading with this adaptation by the Coastal Master Plan that came out in 2017, as well as a set of geotechnical design guidelines that we're working with here in Louisiana. They came out in July 2015 when they were published, and they allow for a lot of latitude in the types of structures that we can be using to protect ourselves from storm surge. So those are the physical changes, but also, you know, $14.5 billion that we got for Katrina, that's not going to be able to, we're not going to get it at a local, state level for all these other projects, which there's multiple, there's hundreds of miles of protection that needs to be in place as the years go on. And then with every, because it's such a fast-growing protection system that's being put in place, it's unprecedented, really. There's also a lot more of oversight and inspection and continuous monitoring that needs to happen with these systems as the years pass this year. So with that, there's going to be changes and adaptations to our geotechnical design. And one particular project, which I'll talk about, is the Falgout Canal project. There wasn't hurricane storm design guidelines that were going to suit our needs. There was one set of guidelines we had from the Corps, which were very, very robust and stringent, but unfortunately they were giving us a design which was unconstructible. So how does the state adapt? In this photo, we're seeing all the way to the right, there is a steel structure that's tying into an earthen levee. On the back side of that structure, it's supported by brace walls like an A-frame. When it ties into that levee with the really soft soils that we have here, we're dealing with consolidation settlement. These piles maybe go down 120 feet, and they're we're putting a levee that we're tying into. These soils are virgin soils. They've never had any kind of weight on them before. We're dealing with a very rigid structure tying into a very loose structure, which isn't really a structure at all. It's just soil. So there's impacts there that we're working with. Then at the steel, as we move to the left, there's the steel wall. This is in lieu of a massive concrete structure. This is what we're using at Falgout Canal. And then on the left arrow, we're pointing to a massive 200-foot wide swing gate. That's just a barge that's floating. When the time comes to close that gate, we're going to, it's going to rotate on a hinge, and it's going to close in, and it's going to stop the surge. In this particular photo, we're looking at Grand Caillou floodgate, and the fore side of the picture where the arrows are coming from, that would be the flood side, and then the protected side is on the background of the picture. For Falgout Canal, we had really weak soils down to 200 feet. We have Holocene, the geology we have. When I say weak, I'm talking undrained shear strengths of 150 to 175 down to about 30 feet. We don't get to maybe 500 PSF until we get to about elevation minus 70. And as you can imagine, it's Louisiana, so everything's from ground level. So elevation 0 mostly everywhere. So it's 70 foot with material at a strength of maybe 500 PSF at the max. To the left, a robust design from the core, concrete seawall, supported by steel H-piles. On the right, an economical design that we can use that doesn't have criteria that we got yet for designing these in the area, is a steel sheet pile wall with steel piles, plumb and batter supporting it. This is a design adaptation right here, and it's been used and it's been successful. And the state's been very supportive in getting behind changing these guidelines so that we can use this. The big difference between the two of these is going to be concrete is going to cost more. It costs more to install, but the steel there's less of a cost for construction. It's also faster for construction time. It requires more O&M though because it's more flexible, which comes into the problem that we had. We were coming up with a design that was steel it was too much flexure, too much movement because it had less rigidity. The core's guidelines were can't have any lateral deflection of more than 3/4 of an inch on the structure. So that was the catalyst for soil structure interaction analysis. But how much should it deflect? We don't really, you can't just say it can go 3/4 of an inch. The state has been helpful in coming out with some other design criteria that we can say, let's use some site-specific lateral load testing, develop our own site-specific PY models. But the unfortunate part of it is standard testing and characterization. We got UU tests, UCs, 1D consolidation, standard practice, but it doesn't yield the amount of soil data results that you're going to be needing to use for a good soil structure interaction analysis. And then for an in-situ test, we are doing cone penetration testing with pore water pressure, but a pressure meter test would be more than suitable for developing PY curves and moduli for using with this FEM models. I'm only showing these two graphs to just demonstrate one thing. Duncan and Buccagnani put together a great play load test project, and they came up with ratios of moduli to strength with respect to overconsolidation and plasticity in 1976. And then Mr. Matlock in Texas comes up with the PY curve for soft clay in 1970. But it's been a long time since 1976 and 1970. There's a lot more information we have that we can use to really economize and reduce the risks with our designs and make them constructible. So here's a picture of the Inner Harbor Navigation Canal surge barrier, similar design, sheet pile wall with battered piles in the back. They did their own lateral load testing at the site on a large 66-inch pile, and they developed, here's a photograph of the lateral load test ongoing. Okay, just two curves here. The top and the orange. The orange is what we would get from a typical Matlock analysis if we were using commercially available programs like LPOD. It's conservative, and it's based on a pile that was 12-inch. These are 66-inch diameter piles. They're in soft soils, I understand that, but when we laterally load test it, we can see that we're getting much stiffer response with respect to the p-value and the py, 25 times stiffer. Get away from the conventional design and get into the site-specific design using this information, using this testing, using lateral load tests. And this was a push that we're making with the state to show them the value of what they get back from this, because this is one site. We can do numerous sites. We can have site-specific data for the southeast Louisiana, and we can get away from using the same Matlock curve that the rest of the country is using, because it's not applicable in all locations. So at Falgout Canal, what did we do? We looked at soil structure interaction analysis of the gate and the brace walls. This is a picture with the gate in the open position, and then this is a photograph of the gate in the closed position. You can see the barriers up in the front. What are we evaluating in this? We're looking at where the sheet pile wall is coming into the receiving structure. We're looking at how much is the sheet pile wall actually going to deflect. We have soils that only have 250 PSF strength down to 30 feet. What's the sheet pile going to do? Is the soil going to yield? If it yields, is it a problem? Can the structure deflect and move with it? All we're trying to show here is that with soil structure interaction analyses, which are not the common way for designing flood protection down here right now, is you can allow these structures to move, you can allow them to deflect, and be within the tolerable limits of still being able to perform for the next 5, 10, 15, 20 years. So we developed a soil structure interaction model with slope W using site data that we had, and we also were able to use the I.H.C. data to calibrate our site to our soil structure interaction model. Like I said, it will perform as we intended. Field measurements, once this gets, the best thing we can do is monitor this as the storms come in, as they go, before, during, and after, to see how it compares to what we were predicting, because these structures are going to be in place for a long time. We're not constructing something and then pulling all of our stuff out and we're leaving. It's going to be there for protection for a long time. So the real thing that we need to be doing is monitoring the equipment and calibrating our designs over the years. That's how way that geotechnical engineers are going to help adapt to the geotechnical design requirements to reduce risk for landowners. Remote monitoring of structures at the tie-ins to the levees. Continuous readings, it's real-time, it's web-based. We're getting real-time notifications. Decisions are being made like in real time, and we're able to advise and communicate the potential risk if there is any. Then we're able to monitor it and see how it's doing during normal periods. So this has been our recommendation to the state, and the state have been they've been very forthcoming with adopting this information. We're able to show that with actual instrumentation, we're able to produce better predictive models and substantially reduce risk and improve the likelihood of these projects for the project stakeholders. Of course, there's an incredible cost economy to it as well. So in general, what we're saying, these are the conversations we've been having with our municipalities, our levee districts, and the elected leaders here in Louisiana, is that not only are we're just used to design and we're building, but we have to get used to including the costs and the concept of watching these structures, because they're living, breathing machines that are going to be going on for a long time. We have to be measuring, we have to be revising our analyses and calibrating it to really truly understand how we're going to assess risk.
Okay, Sean, thank you. Are there any questions that you'd like to answer at this point? We're getting close to the end of our 2 hours. Are there any?
One question there says what soil models we use: more Coulomb and hyperbolic elastic for our finite element modeling, and we use sigma W to do that.
Okay.
And the lateral load test, we're not done at this site, but the lateral load test done at the I.H.C. was done on a plumb pile. There wasn't done one on the battered pile.
Okay. Okay, well, I've been told by our moderator that we can go over time if we would like to. So, Pirooz and Babak, are you still available? Could you push your slides, and maybe in the next 5 minutes, if you would like to wrap up your presentation? I apologize for that. Okay. Well, I think that they might have left us. So again, I'd like to thank everyone for participating with us, and remind you all that Hayward Baker has been our gold sponsor for this event. And we're very appreciative of their participation. Also, that DeepX has been a silver sponsor for us, and as you saw, several of our presentations had people that have used the DeepX software. We also are grateful to Haley and Aldrich, who has also been a silver sponsor, and they have a very large engineering and scientist pool of talent in their offices. And we'd also like to remind you that we had two bronze sponsors, G2 Consulting Group and Itasca Consulting Group. So this concludes our web conference this year, and we hope that you enjoyed it, and we look forward to presenting another web conference next year. Thank you very much.